Hi, welcome to another edition of Linear Algebra. We were talking about applications of linear systems and we came to a case of basic electrical networks. We covered the basic material and then we said we are going to look at a Wheatstone Bridge and how to solve that problem. We talk about the first four items. Then today we are going to do a more extended example of electrical networks. So let's go see what we mentioned last time. So Wheatstone Bridge, something that you probably see in your circuit class, or perhaps you have already seen it in your high school science classes. Today what we are going to see is how do we apply Kirchhoff's laws to find the currents and other attributes of this particular circuit. So first of all, why is this famous and why is it having a name attached to itself, Wheatstone? Wheatstone was the second person who worked on this thing, improved the design, and it was a device for measuring electrical resistance of an object. So it gave a very precise answer compared to the other available things at that time, and so it's a mainstay of many introductory electronics classes or electrical engineering classes. Okay, so what we have here is some battery, and then you see two resistors here, another two resistors here, and then there is this bridge in between. Perhaps if I show you a picture of this thing, animation of it, it might help. So let's go ahead to take a look at that first. So I have something prepared here for you. Okay, so when you go to PHET and then you want to do some basic electrical simulation, you have a set of objects here you can choose from. We're just doing basic circuits, so we have wire and battery, resistors, or if you wish, light bulbs instead of resistors, and a switch. So you can choose these elements and design a circuit and measure a variety of properties of the circuit. For example, you can measure the voltage or the current. So I have a battery here. Let's say it's 10 volts. It's connected to 5 resistors, 1 and 2 on this branch and 2 and 1 on the other one, and the bridge has a resistance of 2 ohms. So the problem is here to find out what would be the current in any of these pieces of the circuit. So if we throw the switch on, this is what we call the conventional flow. So conventional flow, the flow comes out of the positive sides, come here and gets split into these two roads or two branches, and then we see that in the bridge section there is a flow going from this point up there, joins the other flow, and then all of this thing comes back to the battery from this side. Okay, so what was the purpose of the Wheatstone bridge? It's for, we said, for measuring the resistance of an unknown object. So in a Wheatstone bridge, one of these four elements is going to be a variable element that you can change its resistance. And what happens is that as I change this resistance here, at some point there will be no current going through the bridge. Okay, if I play with the resistor here at some value of resistance, what happens is that the potential or electrical potential between these 2 points becomes 0, and no flow is going to occur. That's for basis of measurement of one of the four resistors that we have in the circuit. So if we have an unknown uh, object, we can put it in the place of this, change the resistance until there is no current here, and at that point uh, what happens is easy to show that the ratio of resistance from this point to that should be same as the ratio of resistance from this point to that one. And as a result of equality of that ratio, you can find a missing resistance. Let's go ahead play with one of these things to see what happens. So keep attention that keep your eye on the fact that the flow on this bridge is going upward. Now I go and perhaps choose this one to change it. Okay, so when I click on that, I have an option and a slider here to change the resistance. For example, I can increase it. You see that as I increase this thing to very large numbers, what happens is in that branch, because of high resistance, there is not much of a flow, but the flow in other segments is still going. Let's go ahead and also reduce it to see what happens. It was originally at 2, so let me go back to okay, it was at 2. Now I go down. It's kind of a little bit hard here to reduce it, but let's go ahead and try. So I go to 1. Now let me use this button so that it will be more sensitive. I came down to 0.9 ohms. You see that the current here is kind of slowing down. Let's decrease it some more. 8, 0.8, 0.7, 0.6, excuse me, 0.5. You saw what happened at 0.5. At 0.5, now there is no current going through the bridge. Once that current stops, what we said about the property of Wheatstone Bridge is going to be correct. The ratio of this to that, 0.5 to 1, is same as 1 to 2. When the ratios are equal, the current here stops. Well, you see that there is no current going. In case you want to play with these instruments as well, you can have a current measurement. You put this thing here, you see that the current is 0 amps. But if you pick it up, for example, put it here, it shows a current of 3.33. So there is current in this wire, but there is no current in the other one. So that is, let me put this thing back. Another device you have is a voltmeter. When this circuit is balanced, what happens is that there is no voltage difference between these 2 points. You see here the voltage difference is 0, as opposed to, for example, across these 2 points in our circuit, there is a voltage difference 6.66 and so on. So you can measure all the properties of the circuit by the simple device that we have. Now the question is, well, how do we do the same thing with linear algebra? If you want to do design, well, you can do it on paper as opposed to in the lab, at least in the simple cases, and that is what the problem we are going to look at here. Okay, let me perhaps redraw this thing so in a little bit bigger maybe, so that we can see what's going on. So I have so we quickly draw this thing. Let me just draw this one as well, and then this is our bridge, and then we have 1 ohm here and 2, and then here was 1, and here is a 2, and here is something that in that problem was a 2. This was 10 volts, and these are measured of course in ohms. So the problem, what it asks us, find the current in all the wiring here. Let's go label them. So this one in your text is labeled as I, and then it's coming to this branch. So this is labeled I2, and we have, excuse me, I1 of course. Oh, sorry. We have I1 comes here, and then it continues. At this point it splits, so let's call this one I2, and perhaps this one we call it I3. I'll come back to explain this I3 later on. So I2 comes all the way to this point, I coming here splitting to I1, and this was I3, so I have to keep this one, say I4. I4 comes here, and then portion of it continues to this section, and let's call this one, say I5. And then I5 and I2 join forces here and come back. And as you remember from the conversation we had last time, always from a node to a node on any wire, the current is a constant. So let's go ahead and label these points. So let's call these things, I'll say my battery at point A. This is node B, node C, node D, and let's call this thing node E. This one is not a node, so, but the textbook has a label for it. Let me erase it so that so intersection of 3 wires gives us a node. Now let's restate that from a node to a node on the same wire, we are going to have the same current. So this I1 that is coming here, when you go across this resistance, is still I1. This I2, by the time it comes down to neighborhood of D, this is the same I2 that is coming down here. And this is I4 and I3, I5. And then here, let me ask you, what is the, how should I label the current here? Again, from D all the way to B, it has to be the same current. There is no change in the current from one to other node on the same wire. So this is still same I. Okay. We had 2 laws from Kirchhoff. So we are talking about Kirchhoff's laws. One was the node law, which is the easier one, and the other one is the potential law, which is a bit more involved. So node laws are very simple. Sum of incoming has to be same as a sum of the outgoing. That's just conservation of electricity and the fact that it's a steady state. So whatever comes in has to be equal to whatever is going out. So for example, we go and here is my node. Let's list the node B. At node B, who's incoming? Well, I is incoming, and I1 and I4. So incoming is I. What's outgoing? From this point, I1 and I4 are leaving, so they have to be equal. This conservation of electricity is not being generated or destroyed or anything. So at point C, who's incoming, who's outgoing? So my incoming is I1, outgoing is I2 and I3. So I1 plus I2 is coming in. I3 is leaving. I come to point say D, 2 and 5 are coming in. Who's going out is just I. And then let's just write node law at point E. We have I4 and I3 coming, so I have I4 and I3 coming in, and what's going out is I5. Okay, so the node law is very easy. Now, two things. One is, well, how do you know that the current is going to flow this way? Why do you assume it's not going the other way? And that's actually the basis of Wheatstone Bridge, that current flips from positive to negative or stops at some point, and that's where you know the relationship between resistances is a particular simple equality of fractions. Well, yes, it's true that when you are doing paper calculation, we don't know what the direction of this current is going to be. So we are going to guess or just randomly assign a direction. So I just draw this arrow, assume that this current is in this direction. I go ahead and do all of my calculations. At the very end, if my current turns out to be negative, it means the assumption has to be flipped. Instead of going this direction, it had to be in the opposite direction. So whenever you don't know which direction the flow is, you just assume something. It doesn't matter really. You assume a certain direction, you do your calculation. At the very end, if your current turns out to be negative, it simply means you had to draw the arrow in the opposite direction. It's as simple as that. So let me just again take you to that little demo that we had. Where was it? Okay. When it is at this critical value of 0.5, the current stops in this bridge. If we go ahead and play with that, instead of 0.5, if I go higher value, you see, as soon as I went to 6 and 7, a current started flowing up. What if I go the other way? So at 5 it stops, and you see at 0.4 the flow starts dripping the other direction. So let's make it less so that we see a faster current going through the bridge. So on the bridge, the current could be in any direction. When we are starting to solve the problem, we don't know, and we just make a guess, essentially randomly assign something here, and then we calculate it. If it turns out to be negative, it simply means that the flow had to be in the opposite direction. Okay, that's issue number one. Issue number two, just as we said before, when we write the node laws, one of these things is redundant, meaning the set of equations that we have are linearly dependent. And this is very easy to see. If you just go ahead, just add up all these equations, what do you see? You have I, and then I want to, I made a mistake here, I guess, this okay, let me, sorry for that. At the node C, I1 is what's coming in, and I2 and I3 are what are leaving. So I noticed that I made a mistake here. You probably were wondering. So I1 is what is coming in, and 2 and 3, the way we have drawn this thing, are what is leaving that point. Okay, sorry for that. So we were saying that these equations are linearly dependent. One easy way to see that is that if you add up all the equations, you get an identity. On the left you have I1, I2, I3, I4, and I5. and on the other side we have the same thing, I 1 2 3 4 and 5. So that's just a, this is always true. You can always assume this is saying something is equal to itself. So if you take that equation and subtract from it sum of 3 of them, you're going to get a fourth one, which means that fourth one would be redundant. So out of these 4, 1 is redundant. You can keep it or you can throw 1 away. Either way, it's fine. Okay, that was the easy side. Now we come to the second Kirchhoff law, which says the sum of algebraic sum of the potential increases and decreases on a loop adds up to a 0. Well, what does that mean? First of all, we see 3 loops here, 3 interior loops. Let me just go ahead and color them. So here's, let's call this thing loop number 1. So we start at a certain point and come back to that point. Here's another loop. Let me do another color here. So suppose I start at this point, go around and come back to the starting point. Let's call this thing, say maybe in this, call this thing loop number 1, and here the yellow one, let's call the yellow one, say loop number 2, and then I'll have the third one I choose a direction and then go in that direction. Let's suppose start at this point, we go around, come back to that location, and let's call that, say, loop number 3. Okay, second Kirchhoff law says if you go on a loop and you add and subtract all the potential gains and losses, by the time you come back to where you started, the total has to be 0, that they're all going to cancel each other out. Okay, let's go ahead and so let me erase this one, make space. Loop L1. We said we start some location. Let's start at this location and come back there. We have a direction of the loop, which is it's at your disposal which way you want to turn. It doesn't matter. We go in this direction, and then we have a standard way of adding and subtracting. If I go from the negative side of the battery to the positive side, I say I'm making a gain of 10 volts. So I write plus 10. Then, if the direction of my loop and the direction of the conventional current here are the same, it means we are losing potential across that resistor. How much is the loss of that potential? That's according to Ohm's law. It's going to be the current times the resistance. So I'm going to write minus 1. This is for this resistance here, and the current is I4. I have gained 10 volts going across the battery, and I'm spending it now. I'm going to lose 1 I4 here. And how about here? How much am I going to lose here? Well, first of all, I'm going in the direction of the loop is same as the direction of the current. I'm going to continue losing, and the amount I'm going to lose by Ohm's law is the resistance times the current. So it's minus 2 I5. How about here? Well, these are plain wire. There is no resistance here. Then the resistance in the wires themselves are negligible. So by the time I come down here, I'm not losing anything on this side. When I hit my starting point, the sum has to be 0. So that's loop L1. Let's go ahead. So it's a good idea for you to perhaps pause this thing and make your guess, write what happens in loop number 2 and 3, and then report back and compare your answer with what I'm going to write here. So it's your choice. Again, let's show the cue that we have here. So the cue is this photo is going to prompt you to take the activity yourself. Okay, now let's go to the yellow loop. On the yellow loop, let's start at the node B, go around and come back. So when I go across this resistance, the chosen direction of the loop and the current are the same. That means I'm going to have a loss there. So I'm going to write the loss minus 2I1. Is that right? I lose this much. I come down on this resistance. Again, the direction of the loop and the direction of the current is the same. That means we are going to subtract. So what am I going to subtract? By Ohm's law, 2 times I3. Now for a change in stuff we have been getting used to. The direction of my loop and the direction of the current are opposite each other. This yellow, I'm going from right to left. In the conventional current here, I'm going from B to E. When they are opposite of each other, that is gain in voltage, like going upstairs and such. So that's going to be 1 times I4. So 1 times I4. I have come back to where I started, and the total sum is going to be 0. Round 3. Perhaps again you try to write the loop 3 yourself and come back. By now you have seen all the possibilities. So our assumption for how we are going to travel on loop 3 is we are going in a so-called clockwise direction. Doesn't matter, whatever you choose is fine. You can go clockwise, you can go counterclockwise. You can start at any point you want. For example, well, down on this side there's nothing happening. Starting at D, the direction of this green loop is opposite of this conventional current. So that's how much potential I'm going to gain. It's going to be 2I5 by Ohm's law. Then from E to C, again, the direction of the loop and the direction of the conventional current, they are opposite of each other. That means you're gaining. So I write 2I3. Then in this segment, the direction of the loop and the direction of the current are the same. That means I'm spending it here. So that's going to be minus 1I2 is equal to 0. I came back where I started. Again, wire itself does not cause any potential loss, because we are assuming our wires are perfect and there is no loss in the wires themselves. Okay, well, that's it. Now somebody might say, well, maybe I want to make a different kind of loop. Maybe I want to go all around. If you write that equation, you're going to see that is an equation that can be obtained by linear combination of these three. It's not going to give you any additional information. Or if you go on a loop like this, that's the sum of loop L1 and L2, that again is like adding the two equations you already have. If you go L1 and L3, that's is equal to the equation you get is the same as what you get if you add these two equations. You can make a big loop here, sum of L2 and L3 and so on. These are not going to give you any additional information. So we just go with the interior loops and then we are done. Now what? Well, now we have three equations here. And 4 equations here. We can put all of them together. This is all of the Kirchhoff's law. One of these is going to be redundant. If you want to throw it away, be my guest. Now we have to write it systematically so that we can approach it by Gaussian elimination method, or if you want to use that software. So somehow in your textbook the very first one doesn't have an index. If that made sense to call this one perhaps I1 and then count the rest of them, but we go with whatever is printed there. So this one is called I. Pretend that's like I0. So I have my variables I. Let's write them in order: I1, I2, I3, I4, I5. So I have 6 variables that I need to determine. So I write my equation. The easy ones are the ones that we had here. We have to bring everything to one side. So it becomes I minus I1, and there's no 2 and 3, so I just put a 0 so I line things up. And then I4 comes to the left, and there's no 0 here either, and the right hand side is 0. So that's my first equation. My second equation is an I1. Everything has to come to one side, either left or right. It doesn't matter which side, so long as everybody is on same side. So there is no I in this equation. There is no I4, no I5. We just make sure that we lined up our variables. And then I have this equation, which is going to be let's bring everybody to the left. So minus I plus so there's no I1, there is a I2, and then there is no I3, no I4, and then there is I5. And then if you want to throw in the last equations, fine. If you want to leave it out, that's fine too. So one is redundant. One equation is redundant. Okay, how about here? Well, let's if you take 10 to the other side, multiply by minus, you'll have I4 plus 2I5 is equal to 10. Only the loop with the batteries on it, there's going to have a non-zero on the other side. This one I'll have there is nothing here. Let's again, I forgot to put 0 so that later on we don't make a mistake. So on loop number 2 I have let me make sure I wrote this correctly. Loop number 2, loop number 2 minus 2I1 minus 2I3 plus 1I4. Is that right? Minus 2I1 plus 2I3 so minus 2I1 minus well, this is 0 minus 2I3 plus I4 is equal to 0. Finally, this is minus I2, so 0 and 0 minus I2 plus 2I3 plus 2I5. That is also equal to 0. So that is my equation. So what do we want to get out of it? Well, whatever the problem is asking us, we essentially want to figure out our currents. Once we have the current, we can calculate a variety of potential drops. That's multiplying the current with the resistance that you have, and you figure out the voltage by Ohm's law. Now this is a 6 by 6 equation. It's going to take a while if you want to do it by hand, so we go and resort to our software. Let's hope that we enter it correctly. So we go to this one, and it was a set of 6 variables. So I'm going to have a crowded picture here, 6, and there's right hand side, so that makes it 7. So let's go ahead and quickly change these. So it's 1, -1, 0, 0. Notice the problem with the labeling in the text. That's your I. That's going to be I1, I2, I3. That's why I didn't like the labeling in the text. So you have to be careful with that. There is a chance that I make a mistake entering all of these. So that's why you want to have some convention for yourself. This is 1, this is 1, this is -1, and that is 0. Next equation is sorry, let me go back here. I had dropped my last node equation. I forgot about that one, so I'm gonna come back here, and I'm gonna okay. I hope that I'm correct. Let's double check before we actually do this thing. So I have 1, -1, and then 0, 0, -1. So these zeros, you match it against what we wrote in our equation, 5, and then here I have -2, 0, -2, and 1, and 0, 0, and then 0, 0, -1, 2, 0, 2. Okay, let's hope that we are correct. So we go to resume. Now we are going to quickly solve this thing by Gauss-Jordan. This is my pivot, and this is my target. So I get rid of that. This is my pivot, and then I click on the pivot and this, and simplify that. Now one of these two entries has to be brought to this location. So for switching, we click on edge numbers, so it's switched. I normalize by dividing by that number, so I divided by -2, use this thing as a pivot, eliminate that one, do another swap, normalize this thing to be 1 so it's easy to follow. This is pivot, this is target. Now this is a pivot, this is my target. I divide this thing, this last equation, by 15, so I know my last current is going to be 3. Now I go backward. This eliminates that, this eliminates that one, this eliminates that one. Pivot, target, pivot, target, pivot, target. Okay, finally pivot and target. So we got our numbers. We have, let's write it down. So what we have here, this was I, if you remember, I1, I2, I3, I4, I5. So I have the currents found now. Let me write it big so that I can refer to this. I is 7, I1 is 3, I2 is 4, I3 turned out to be -1, I4 turned out to be 4, and I5 turned out to be 3. So 7, 3, 4, -1, 4, 3. We are done. Let's write down what we got. We got I is equal to 7, I1 is equal to 3, I2 is equal to 4, I3 is equal to -1, I4 is equal to 4, I5 is equal to 3. What are the units? These are measured in amperes, or you abbreviate it to amp, or just sometimes you just write an A. What does negative mean? Negative means our assumed direction of the conventional current is not right. If this is -1, it means that the conventional current was going this way, not in that direction. So we said the algebra comes out and figures out what direction is current going to have, and so we are set with that. Now if you want to find out the voltage drop from one node to another one on one of these branches, you simply multiply the current and the voltage, and then you will have the information. Of course, in your circuit class, you're going to look at this problem from a much more sophisticated point of view. You're going to have many other elements thrown into the picture, but right now we are just explaining that when you want to solve the majority of problems in the sciences, at the first level you come across a linear system to solve. Why do we have systems? Because we have interaction of variety of components. So for example, here we have a current coming and splitting, and there's a conservation law that holds about these things. That's our node law. As soon as you have a relationship between neighboring elements, you have a beginning of an equation. In the simplest case, it's just a linear equation. Here's another example of a balance equation or conservation. By the time you come back, the total potential change has to be 0. That gives you some other equation. When you put all the equations together, you get a system. So system represents presence of multiple components. Linear system means the simplest kind of view we can have on the universe, where the relationships are just a linear equation, mx plus b type equations. So we have advertised where the linear systems come from. Of course, in applications, size of linear systems are substantially bigger than the problems we are doing here, and so we need to have a good understanding how the systems behave, so that we understand the solution and that we use it to design our equipments and such. Okay, I guess I'll be going on to the some future topics from the next section, and perhaps if you have time we come back to linear economic models and finite linear games if you get to have the time to come back to them. Okay, until the next lecture, good luck and God bless.